flip out to go have your photo shoot. All right, so there are, in general, we can classify discontinuities as two types of discontinuities. So we did discontinuities in pre-calculus, and I think I have started using this language, so you should have seen this before. There are removable discontinuities and non-removable discontinuities. Basically, there's only one way you can have a removable discontinuity, and that's just to have a single hole in the graph. So a removable discontinuity, if you're graphing it, just to draw like an example here, is just a hole in your graph. It is called a removable discontinuity because we could fix it by putting one single point right there, right? If we just add a single point at that, where we have that hole, we no longer have a discontinuity for this graph, right? Graphs have discontinuities if at any point while you're tracing the graph, you would have to pick up your pencil. So as you trace this graph right here, to get over that hole, you'd have to pick up your pencil, jump over the hole, and keep going, right? Theoretically. I realize you get infinitely close, so. But theoretically, you'd have to pick up your pencil so that you had that hole in the graph. Okay? The language that AP is going to use most of the time, possibly all of the time, is removable discontinuity. Some other things that you will see it called as a hole, you may see point discontinuity. Also, that's a possibility. But as far as the AP exam goes, I think they're pretty much always going to call it a removable discontinuity. I don't mind if you call it a hole, that's fine. But you need to know that phrase, removable discontinuity. Non-removable discontinuities can look a few different ways. In general, they're jumps or vertical asymptotes, or a combination sort of the two. So a jump in the graph would be something like this, where you just kind of are at one value and you jump up to another value. That would be a jump. It is considered a non-removable because you can't fix it with one point, right? Or vertical asymptotes, really of any sort. So it could just be, it could be that they both approach positive infinity. That's still a discontinuity, right? Even though you're both approaching positive infinity, you have to pick up your pencil at the theoretical infinity here, move over to the right just a little, and continue. So any type of vertical asymptote is going to cause non-removable discontinuity. So, let's talk about discontinuities. There are many things that can cause discontinuities. These are a few of them. I think it is what we'll mostly see. Negatives under a square root. You cannot have negative numbers under a square root. Zeros in the denominator of a fraction. That one's going to be a big one. A number less than or equal to 0 inside of a logarithm. That won't happen as often, but it does cause a discontinuity if you have negatives in a logarithm. One we'll see quite often as well is a piecewise function that has a hole or a jump. And then there are some trig functions that have discontinuity sort of built in. They are tangent, cotangent, secant, and cosecant. If you remember those graphs, we didn't spend a lot of time doing those graphs, but all of those graphs have vertical asymptotes at periodic intervals there. We probably won't see a ton of those either. The main two we're really going to see are right here. Zeros in the denominator, piecewise functions with a hole or a jump. Those are the big two that we're going to see. So what you're going to be asked to do today is to look for discontinuities and tell whether they're removable or non-removable. Okay? So, we did this some in pre-cal. Does anybody remember what makes a discontinuity removable whenever we're talking about rational functions? So functions like we see right here for number 1. Good. If factors cancel, it's a whole. If doesn't or does not cancel, that's a vertical asymptote. So for rational functions like we see here, we just want to factor. So x plus 3. I could factor this like it is. It'll be a little easier to factor if I factor out the greatest common factor first. So factor out that 2, you'll get x squared plus x minus 6. And that'll factor into x plus 3, x minus 2. So, you must remember that, let's put a little note right here, discontinuities only come from the denominator. Maybe it might help you to remember discontinuity and denominator both starting with D. We only look at the denominator to tell where our discontinuities are. The numerator just helps us decide what type of discontinuity we have. Okay? So, like for this problem, I would know here at x plus 3, right, that cannot equal 0, so at x equals negative 3 and x equals positive 2, I have discontinuities at those points. Okay, so those are my discontinuities. Alright, I have discontinuities at x equals negative 3 and x equals 2. I know that because when I factor, that's what's going to give me 0 in the denominator. But then I do care about the numerator to see if anything cancels. And does anything cancel here? X plus 3 will, right? So if it cancels, that tells me that I have a removable discontinuity, whereas at x equals 2, this is non-removable. Specifically, it is a vertical asymptote there instead of a jump. Like a symbol for that, or
like circle 1 square line.
I don't think we did that in here. I'm not familiar with like any standard notation for that. It could be something another teacher did, but I'm not familiar with any notation like that that would be like accepted on the AP exam.
Teachers, at this time, I need 10th graders with the last name F through L. Thank you.
Okay. All right, so if we factor the second one, we would have x plus 2, x plus 3. In the denominator, I would have x plus 1, x plus 3. And I haven't noticed anybody that has trouble with factoring yet, but you guys hopefully are seeing how well you need to be able to factor here, because it shows back up a lot. So remember, only look at the denominator. So my discontinuities are going to be from the denominator x equals -1 and x equals -3. Okay, now I do have one of these that will cancel. So at -3, what type of discontinuity do I have? It is a removable. And at -1, that does not cancel, so I have a non-removable, specifically a vertical asymptote there, if they care. What about that x plus 2 in the top? What did I do with it? Is it going to cause a discontinuity from the numerator? It is not. So it's just extra. It's just left over, right? So we don't do anything with that. A lot of times I see students trying to use that for something. It's from the numerator. The only reason we even care about the numerator is to tell us whether it cancels or not. So we don't use anything here. All right. Okay. Problems like example 3 show up fairly often. And it's a specific type of problem that you'll see. This almost cancels, right? I got an x plus 1 on top, an x plus 1 on the bottom. It almost cancels. But in the top, I've got absolute value bars. In the bottom, I do not have absolute value bars. So we've got to kind of think about what this graph would look like if we had something like this. And a lot of times this will show up non-calculator, so you cannot graph it to tell what it looks like. If it's calculator active, yes, please graph it. It'll be easy to see what happens there. But I do know, just from looking at this graph, that I've got x plus 1 in the denominator. So I'm going to have a discontinuity at x equals -1. I know I have to have that discontinuity because I have an x plus 1 in the denominator. If I plug in -1, it's going to give me a 0 in the denominator. So there's definitely a discontinuity there. The question is what type is it? Do these cancel or do these not cancel? So if you think about what's happening here, let's think about plugging in some numbers like from the left and the right. -1 is the number we know is going to give us a 0 in the denominator. So if I pick some numbers lower than -1, like -4, right? -4 plus 1 over -4 plus 1 would give me absolute value of -3 over -3. What will that be? 3 over -3, which will give me -1. All right, so I'll get -1 here. -3. I'd have absolute value of -3 plus 1. -3 plus 1. That gives me absolute value of -2 over -2. That gives me -1 again. Right? What's going to happen with -2? Basically the same thing, right? I'll get 1 over -1. I get -1. If I get to -1, it's going to be undefined because of that 0 there. Even if I plug in decimals, like -1.5, the same thing's going to happen. I'll have positive 0.5 over -0.5. I'm getting -1 for every value all the way up until -1, right? But what's going to happen whenever I go to numbers bigger, like 2? I would have absolute value of 2 plus 1 over 2 plus 1. That'll give me absolute value of 3 over 3. What will I get? Positive 1. And same thing's going to happen for 3 and 4 and 5. I'm going to get positive 1. So if I graph this, I'm going to show you what it looks like on Desmos just so we got a good picture, even though this is not usually calculator active. Here, this is what it's going to look like. It is going to be a horizontal line at -1, and then it's going to jump up to +1. So you have a jump at that point. Desmos doesn't graph open circles, really, but you have open circles in both places because it's undefined there when you got 0 in the denominator. So, if you see something like this with the absolute value where it almost cancels but doesn't quite, this is going to be a non-removable and specifically a jump in the graph. All right, questions on that? If you see absolute value bars, that's usually what's happening. It's a question like that. You can think of plugging in some numbers. It's usually going to be a jump. Example 4, ask us to do a composite function, f of g of x. So first let's find f of g of x. So f of g of x means that I'm taking g of x and I'm plugging it in for the x in the f function. So that will be 1 over x squared plus 3 plus 2. And so that's just going to be x squared plus 5. All right. Obviously nothing's going to cancel here, so whatever discontinuity I might have is going to be non-removable because nothing's going to cancel with that numerator. So I know this denominator cannot equal 0, right? Does x squared plus 5 factor? It will not factor, not with real numbers anyway. So I can try it this way. X squared plus 5 cannot equal 0. And I could try solving it, but I'd have to subtract 5 from both sides. So I'll get x squared cannot equal -5. And I'll square root both sides. But what happens when I have to square root both sides? I get an imaginary number. X cannot equal plus or minus I square root of 5. And that's an imaginary number. We're talking about the graph of this function, right? So imaginary numbers don't show up on graphs. So this is not going to be an answer for us. Is there any number I could plug into that denominator that would give me 0? Okay, what do we know about x squared when we plug in anything? It's positive. And then we're adding 5 to it, right? So whatever's in that denominator has to be positive. Because when we square whatever number we plug in, it becomes positive. And then we're adding 5 to it, which just makes it a little bit greater, but still positive, right? So, so there is nothing that's going to give you a 0 in the denominator here. So this one, the answer for this is none. So if you get a denominator like that where nothing will make it 0, even though there is a denominator, it will never equal 0, then you don't have any discontinuities. And typically it happens when you have a square somewhere. There. Okay, questions? All right, next we're going to look at some piecewise.
At this time, I need 10th graders with the last name M through R, and it's seniors with the last name M through N. And so these are seniors who did not have their photo taken. So it's seniors last name M through N, and 10th graders M through R. Thank you.
All right, so for this, I would like for this particular one to graph it, and then we'll talk about how we can do it without graphing. So how do I graph x over 2? What type of graph is it going to be? What's it going to look like? It's much easier than it appears. The fraction is deceiving. It is linear. X over 2, that x has an invisible 1 in front of it. It can be written this way, 1/2 x. Right? So it just has a slope of 1/2 and a y-intercept at 0. Right now I'm going to graph the whole thing, but we're going to have to erase some of it. So if you're not doing this in pencil, I wouldn't do exactly what I'm doing right now. So I've got, this is the graph for x over 2, but I need to look at -5 right here, and I'm gonna draw myself a little dotted red line. This is not actually part of the graph, and I'm gonna cut off this graph right here. I only need to use the part to the left there. Should I use an open circle or a closed circle at the end of this graph right here? Open. Because I have a less than sign right there. Okay. What about absolute value of x minus 1? What does it look like? What absolute value graphs look like? They're V's. What's that minus 1 do to it? Not left. Right. It's going to go to the right one. So this is going to be a V shifted to the right one. I'm going to need a closed circle right here. This time we need to stop at 3, positive 3. And open circle for that end right there. Again, these dotted lines are not part of your graph. I'm just drawing them for us to picture those sections of the graph that we're sectioning off. So we got this left side over here. We got that middle section. Now we're going to work on this right-hand side. What do square root functions look like? They look like this. You know, if you're unsure, you can just plug in numbers, right? So if I plug in 3, I got 2. So the 0.32 is where we need to start right here. Oh, look. It is the same. So we had an open circle, but it's being filled in by a closed circle, right? And then if I plug in 4, you know, if you think about doing a table here, if I plug in 3, I get square root of 4, which is 2. But if I plug in 4, I'm going to get the square root of 5. We're doing this without a calculator. We don't know how to graph that. So 5 would be square root of 6. Can't graph that. 7 would be square root of, hold on, 6 would be square root of 7. 7 would be square root of 8. I'm writing these down, but 8 would be square root of 9, which is 3. So 8, 3 is probably the last thing that's going to fit on the graph anyway. So I've got this curve that looks like this. Yes?
How would it be a golden circle if either one of them?
Oh, thank you. I was making assumptions of the way that things normally are. Bo is right. Right here, we have a less than sign. We also have a greater than sign here. We don't have or equal to for either one of them, so I've messed up. That should be an open circle right there. A lot of times you have open circles filled in by closed circles, but that is not the case here because both of those are actually just less than or greater than signs. So you were right on that one. So we would have 2 discontinuities here. We would have a non-removable at x equals -5. Specifically, if we want to be very specific about that, it is a jump discontinuity. And then we would have a removable at x equals 3. If we had an or equal to with one of those, where we did have an open circle filled in by a closed circle, you wouldn't have a discontinuity at all at that point. Okay, now let's look at how to do that without actually graphing it. Because you can see here, we have trig. We did learn how to graph trig functions, but I'd rather not if I don't have to, right? I also gave you this one that's got this little bit of different thing happening here where they gave you this weird notation for this. So in Math 3, you're supposed to learn how to solve absolute value equations. So if you have absolute value less than a number, that's an AND problem. If you have absolute value of something greater than a number, that's an OR problem. So when I see absolute value is less than 1, I could rewrite it this way. X is less than 1 and x is greater than -1. So the first time you write it, you leave it exactly the same. The second time you write it, you're going to change the sign and flip. You change both signs. You flip the inequality, you change the sign here. For this one, it would be x is greater than or equal to 1, or x is less than or equal to -1. When I used to teach these, I would say that less than sounds a little like and. Greater sounds a little like it's got or in it, although it's spelled that way. But so let's think about where these numbers are on a number line. Like if you're thinking about a number line, I've got -1 and +1. So if I've got numbers less than 1, but also greater than -1, it's the numbers in between -1 and 1, correct? So another way I could write this here if I wanted to is I could write it -1 less than x less than 1. It's the numbers between -1 and 1. Now, when I think about these two parts, you've got x is greater than or equal to 1. That's the numbers up here. And then you also have the numbers less than or equal to -1, so that's the numbers down here. So what I like to do with these is I like to rewrite them so that I'm looking at the like 3 separate sections here. So I rewrite it like this. The lowest section that we're looking at here are the numbers less than or equal to -1. The function we use for that is x. So x, and then we would say x is less than or equal to -1. This middle function, cosine of pi x over 2, that is from -1 less than x less than 1. And then you'll see x again when x is greater than or equal to 1. I have not seen this notation with those absolute values used a lot, but I have seen it. So I wanted to go over that here. A lot of times they'll just give you the function where it looks like this from the very beginning. Okay, so if we want to do this without, actually having to try to graph this, what we really are thinking about doing is we're doing the limit as x approaches -1 from the left of f of x. So the leftmost function right here at -1 is x, right? So if we plug in -1 for x, we just get -1. But from the right, limit as x approaches -1 from the right of f of x. So from the right-hand side, these two functions right here come together at -1. We would be using the cosine pi x over 2. So we would be doing cosine of pi times -1 over 2. That would give us cosine of -pi over 2, unit circle. -pi over 2 would be right here. That's 0, -1. Which one is our cosine? This is 0, so we would get 0. So what does that tell us if our limit from the left is -1, our limit from the right is 0? That's a does not exist for our limit. There's a jump. So we have a non-removable at x equals -1. Now we also need to check the same thing at +1, right? Because +1 is another place where our functions come together. So if I do the limit as x approaches +1 of f of x, from the left you're looking at cosine. So it's cosine of pi times 1 over 2, which is cosine of pi over 2. Pi over 2 is right here. That's 0, 1. What's the value for that? It is 0. Limit as x approaches 1 from the right of f of x. We just be plugging into that x right there, so we just get 1. Do I have a limit there? They do not match. So I would add to this end x equals 1. You've got to jump in the graph because those limits are not the same from both sides. If you get the same number, if you get 5 and 5 from both sides, then that limit exists. So there's not a discontinuity unless you have two open circles, right? And you wouldn't have two open circles for one like this. Here. Okay, questions on that? All right, we don't have time to do this one, and I don't like it anyway, and we'll do those tomorrow. All right, so assignments for this. I think I need to adjust what is on Canvas just a little bit. Let me see what numbers it gives you there. Let's see. Canvas. All right. 96. 37 through 55 on. Actually, that assignment didn't have, I think I just haven't fixed those notes. I should have taken those last couple of questions off of it because that's actually the removing discontinuities is later. So actually, we're good here for this. So we actually finished everything we needed to. I need to take those last ones off. And you should be okay on these, I think. 37 through 55, but the odds only. Okay, answers are in the back of the book, so you can check as you go. Yeah, odds are in the back of the book, so check your answers. We'll go over those tomorrow. Yes, I'm getting ready to post it. Yes, I'm going to do that right now.